Hi guys, welcome back to my channel. If you are new here, I am Rusiru, a software engineer. In this video, we will learn network types, topologies and devices. Let's start by understanding the hierarchy of networks. At the smallest scale, we have personal area networks or PANs. This is your immediate digital bubble, typically just a few meters around you. When your Bluetooth headphones connect to your home or your smartwatch syncs with your laptop, that's a PAN in action. It's personal, it's close, and it's designed for your individual devices to talk to each other. Step up one level and we enter the world of local area networks or LANs. This is probably the network you are connected to right now in the building. LANs cover limited geographical areas. Think of your home network, your office, or the campus. The key characteristic here is speed and local efficiency. Because everything is relatively close together, LANs can achieve very high data transfer rates. We are talking 10 to 1000 megabits per second. That's why transferring files between computers in the same office is so much faster than downloading from the internet. Moving outward, we have metropolitan area networks or MANs. These span entire cities or large metropolitan areas. Think of a university with multiple campuses across the city, or city government connecting all of its offices. MANs are essentially multiple LANs linked together across a broader geographical area. Finally, at the largest scale, we have wide area networks or WANs. These are the networks that span countries, continents, and ultimately connected to the form what we know as the internet. Large corporations use WANs to connect their offices worldwide, and internet service providers use WANs to bring connectivity to your local networks. Here's the key insight. This hierarchy isn't just about size, it's about optimization. Each level is designed for different priorities. PANs and LANs prioritize speed and direct communication. WANs prioritize reach and connectivity, often accepting some performance trade-offs to achieve global scale. Now that we understand the scale of networks, you might be wondering, how are these networks are actually structured? What does the architecture look like? That brings us to the network topologies, the different ways we can arrange and connect devices within these networks. Now that we understand network scale, let's dive into network topologies. Essentially, the architectural blueprints for how devices are connected within a network. Think of topology as the floor plan of your network. Let's start with the bus topology. Imagine a single highway with all houses connected directly to it. In networking terms, this means all devices share one common communication channel, typically a long cable. Data travels along this cable and each device checks if the data is meant for them. It's beautifully simple and cost efficient for small networks. But here's the catch. If the main cable breaks anywhere, the entire network goes down. It's like closing the only highway, everyone is stranded. The star topology solves many of these problems and is what you'll find in most networks today. Picture a wheel with spokes. Every device connects directly to a central hub or switch. All communication must pass through this central point. The brilliance of this design is isolation. If one computer fails or its cable breaks, it doesn't affect anyone else. Adding new devices is straightforward, and troubleshooting becomes much easier. However, that central hub becomes your single point of failure. If it goes down, everybody goes down. Ring topology takes a different approach. Imagine devices sitting in a circle, each connected to exactly two neighbors, forming a closed loop. Data travels around the ring, typically in one direction, with each device processing and passing it along. This creates very predictable data flow and minimizes packet collision through token-based protocols. But like the bus, one breaks in the ring can disrupt everything. Finally, we have mesh topology, the most robust but also the most complex and expensive. In a mesh network, devices have multiple connections to other devices, creating a web-like structure. This is how the internet backbone operates. The beauty of mesh is redundancy. If one path fails, data can take alternative routes. It's like having multiple highways between cities. The downside, cost and complexity skyrocket because you need many more cables and network ports. Here's a crucial insight. There's always a trade-off between simplicity, cost and resilience. Bus and ring are simple and cheap but vulnerable. Star provides a good balance of manageability and fault isolation. Mesh offers maximum reliability but at significant cost. Network architects must choose based on their specific requirements for uptime, budget, and complexity tolerance. These topologies are just the structural foundation. To actually move data across these networks, we need specialized devices, each designed for specific functions within our network architecture. Let's explore the essential networking hardware that brings these topologies to life. Each device that we discuss has a specific job, and understanding their roles is crucial for any software engineer working with network applications. Let's start with a comparison that reveals how networking intelligence has evolved. Hubs versus switches. A hub is basically a dumb multiport repeater. When it receives data, it broadcasts that data to every single connected device. It's like shouting in a crowded room. Everyone hears everything, whether it's meant for them or not. This creates what we call a single collision domain, where all devices compete for the same communication channel. A switch, on the other hand, is intelligent. It learns and remembers the MAC addresses of connected devices and forward data only to the intended recipient. It's like having a smart portal system that knows exactly where everyone lives. This dramatically improves network performance and security by reducing unnecessary traffic and preventing eavesdropping. Routers operate at a higher level. They are the traffic directors of the internet. While switches work within a single network using MAC addresses, routers connect different networks using IP addresses. They maintain routing tables and make intelligent decisions about the best path for data to travel. When you send an email from your office in New York to a friend in Tokyo, multiple routers make forwarding decisions to get the data across the globe. Bridges serve a more specific function. They connect two LAN segments that use the same protocol. Think of them as translators that help different parts of the same network communicate effectively. Modern multiport bridges are often just called layer 2 switches. Firewalls are your network security guards. They monitor and control traffic flow based on predetermined security rules. They can block unauthorized access while allowing legitimate traffic through. Modern firewalls operate at multiple layers of network stack, providing sophisticated protection against various types of cyber threats. Modems, short for modulator demodulator, are the devices that convert digital signals from your computer into analog signals for transmission over cable or telephone lines, and vice versa. They are your gateway to the internet through your ISP. Finally, access points extend wired network into the wireless realm. They create Wi-Fi networks that allow wireless devices to connect to your wired network infrastructure. Here's the key insight. Each device specializes in specific layer of network communication. This specialization isn't accidental. It's fundamental principle that allow network to be efficient, scalable, and maintainable. Different devices handle different concerns from physical connectivity to security to routing. These devices work together beautifully, but they need a common language and framework to communicate effectively. That's where network communication models come in. Standardized approaches that ensure all the different devices and protocols can work together seamlessly. Let's talk about OSI model and TCP/IP in the next video. If you have any questions, please leave it in the comment section. Don't forget to like and subscribe as we are continuing this series and building a solid knowledge on system design. I will see you in the next video. Thank you for watching and have a great week.